Alright, semiconductors now, semi. Alright, understanding power transistors, breakdown parameters, introduction among electronic parameters, bipolar transistor breakdown related to one of the most critical measures of matter of fact with this breakdown voltage pretty high instantaneous power dissipated during the test must be accurately controlled to avoid a local hot spot on the chip. On the other hand, the breakdown mechanism from the highest frequency oscillation care must be able to accurately measure the parameter of this application. Now give the definition of the breakdown parameters associated to physics with semiconductor devices. Chapter describe the test techniques and methods recommended to perform the kind of measures. Some of the most high voltage power bipolar transition negative positive negative type analysis carried out on this note will be referenced to the negative positive negative device as well as the positive negative mechanisms are essentially the same as the reverse polarities of all bias breakdown mechanism. Let's first consider the collector and the base junction. Like the positive and negative diode, the avalanche process limits the collector base voltage than the transistor can sustain. Voltage large enough that the negative side depletion region will reach the negative positive contact diffusion. If the voltage increases further, the contact will supply electrons to the positive and negative junction. At this point, the collector base junction is essentially shorted and the current is limited with external resistance. Because there are three mechanisms control of the breakdown: thermal instability, tunnel effect, and avalanche multiplication. Thermal instability. The breakdown thermal instability will result in a large increase of leakage current with the junction and the temperature increase of the germanium based devices more sensitive to the mechanism compared with the silicone. When the process snowballed, the current increased yield in higher function temperature, which can lead to the destruction of the chip that extends above the melting point of semiconductor material. Tunneling effect. With an electrical field approach of 10 to the 6 volts of the centimeter in silicon, the significant current begins to flow with the means of the band tunneling process. To get such a high field, the junction must have a relatively high doping concentration on both sides of the positive and negative junction. As a matter of fact, the field may also be that creates enough force on the covalently bonded electron to free with the creative of the two carriers of the whole of the electron contributed to the current with the energy band of the point of view of the breakdown process. The electron makes the transition valency bond with the conduction band without interaction with any other particle. The breakdown mechanism silicon device breakdown voltage lower than 4 EGQs comes with a tunneling effect. The function breakdown voltage excess of 6 GEQs. The mechanism is generated avalanche multiplication. The voltage from 4 EGQs to 6 EGQs. The breakdown of the combination two effects. Since the energy band in this silicon decreases with the temperature of the breakdown voltage due to the tunneling effect in the semiconductor negative temperature of the coefficient of the temperature effect can be used to differentiate the tunnel effect from an avalanche mechanism. The positive of the temperature coefficient, one of the most point of tunneling effect of the dominant 0 voltage 5 volt to 6 volt range. Mechanism is not present with a high voltage junction since the doping concentration is too low to generate a tunneling effect. Avalanche multiplication, a mechanism also named impact ionization, the most important junction breakdown since avalanche breakdown voltage impose upper limit of the reverse bias on the collector voltage value which the breakdown occurs that depends on the structure of the junction, doping, concentration, manufactured transistor. Both the structure and epacity can be controlled and breakdown voltage given in the semiconductor with a reasonable predictable of the design stage. In this process, free carriers can gain enough energy from the field between collisions to break in covalent bonds into the lattice when they have collided with it, and consequently every carrier interacting lattice creates the two additional carriers. The mechanism snowballs. Three carriers can also be participate to the collision. This leads to a sudden multiplication carrier space for a charge region when the electrical field becomes large enough to trigger the avalanche. Let's also consider the electron traveling a space charge reverse region, reverse bio positive negative junction electron travel to have an average distance L, the meaning of the free path, before losing energy interacting at an atom lattice. The energy gained from field E with the movement electron between collisions. So we have the energy gain is equal to the quiescent of the limited series energy dx. Alright. I don't know where to start. We'll read from the top. Assume the electron accumulated energy from the field prior to the colliding atom The bond between the atom core and the one over the bond of the electron can be broken during the collision. This creates three resulting carriers, which are free to leave the region of the collision. Simplified schematic representation in Figure 1. So Figure 1 says simplified representation avalanche process of the junction. Reverse bias, free electron. Note drilling is not the skill. Electrical field, extra electronic hole, collision, collector base space region. Near the edge of the space charge region of the electrical field, low, in particular, no carriers are gaining enough energy within the field to create a whole electron pair before the loose of the kinetic energy and collision with the lattice. Consequently, avalanche is confined with the central area of the space region with the field size. This is representative of the Figure 2 of the central region being identified. So B shows ionization of the high field area X1 space charge region, and then we have carriers or pairs created with the region DX and X, electrons flowing from left and hole falling from the right. Let's consider the number of carriers created with the avalanche small volume of the width dx located with the x1 and figure 2b. Low let number n number 0 no density of the electron entering x1 from the left to xa with the avalanche phenomena will increase the density with xa to xc, and then when wave of the electrons entering the volume with a dx and x lefting of the density of the end of the density of the electrons entering the negative net electrons, probability of electrons creating electronic hole pairs traveling from dx given with a product of the ionization coefficient time length of the dx, and if the electronic gains energy more rapidly, field is higher. And ionization coefficients of the function of the electrical field, hence for the position of the semiconductor of the chain, many of the density hole will increase the consequence of the avalanche. For the AP, the factor represents ionization coefficient for the holes. Let NF be the density with the electrons reaches the capacity, X capacity, NF density with the electron, NO plus 1, NM1 plus SN2, N2 density with the electrons created with the X and XC. Since the electrons holes are created within pairs, N2 is equal to P2 with a maybe right, assuming that AN equals AP. We can write equation 3. Ratio density of the electron leaving supercharged region. Density of the NO is called the multiplication factor. As integral to the denominator, equation 5 approaches the M factor, multiplication factor increases to infinity, therefore avalanche will occur. So XA, the XC limited series of frequency DC X1. Alright, IC and BVCBO. Under breakdown, emitter current is not affected. The density of the ionization level collisions at X is not proportional to X. The wildcard represents the density of the excited with the electron arriving at X with enough energy to create the electronic hole pair. The density N is termed the total electron density with the N times the probability of the electron not collided with the distance necessary to get the right energy. The length of D is derived with equation 1, letting E1 being the minimum energy necessary to create the ionization, and E being the average field of the accelerated electron. Alright, some ionization coefficients depend strongly on electric field multiplication factor increasing rapidly with the field. Consequently, small increases field is the voltage approach breakdown called with the sharp increase the current observed with the curve tracer. Not only do the ionization coefficients vary fieldly, hence for the position space of the charge region, width of the space charge region varies with the voltage. Therefore, evaluation M with equation 5 with difficult good approximation can be derived with a simple equation 9. VR is the reverse broke down applied cross function. BV is breakdown voltage. In common base configuration, breakdown to the impact ionization avalanche, and giving a well-defined voltage depicted with the figure 3A with the effect of the current coming from the emitter having little effect on the breakdown. From common emitter configuration, breakdown not sharply reflective of the transistor output characteristic in figure 3B, a curve with low voltage of BVCEO with the configuration source soon. Impact ionization process, secondary hole injected with the base, yielding base current with the turn leads will increase the emitter current with the current runaway with eventually a curve with the mechanism snowballs. Ionization mechanism essentially caused by the temperature effect with the time delay following when the pulse of the BVCEO is applied with the transistor device. It goes back to the second avalanche area with during the time when they elapse the avalanche. The second breakdown junction unstable rapidly downgraded. in particular resistant breakdown spot, and extremely low during the third party of the curve of the voltage significantly reduce the tip of the high temperature of the semiconductor intrinsic mode near the breakdown spot location. Currents keeps increasing, silicon melts, and transistor permanently destroyed. Your second breakdown. Use of power transistor limited with the second breakdown phenomena that abrupt with the degree of the device of the voltage capability simultaneously internal constriction of the current. Figure 4 shows the typical amp current, voltage current, characteristic transistor second breakdown of the avalanche breakdown, also named first breakdown, a curve of the voltage applied with the junction reach of the value specific to the device is discussed above. The voltage is increased with the second voltage occurs. Figure 4 shows typical second breakdown characteristics. Basic power transistor geometry. Simplified cross-section power transition given in Figure 5 illustrates the main areas involved in the breakdown process. Voltage rises across the transistor electric field sustained with a negative impacticity depleted region increasing according to one of the most output region. Reality monitor transition not built with a single junction depicted in Figure 5 with several emitter strips that diffuse the base P. Such technology is mandatory to explicit state with the dynamic characteristic result of today's application photo given with the illustrative concept. Shows an ammetric contact emitter base, silicone collector base depletion region, collector, and substrate. Figure 6 shows a photo of a typical power transistor planar termination, base and emitter. On the top of the electrical field, not collapse over the edge of the chip with the base diffusion no longer exists to prevent the mode of failure. Transistor is designed with a junction termination suited with the kind of device or development of junction termination. Example is Figure 7. Typical planar junction, emitter base collector substrate, silicone POS guard, negative positive, chip end glass silicone. A type of printing document planar must be Webley technology manufactured power transistors. However, MOT termination is still used with a very high voltage with BVCPO at 1500 volts and above. Alright, dynamic braking characteristics. Although the static breakdown characteristics are valued with the defined performance of semiconductor devices, do not provide all information needed to safely use the power transistor. Leaving aside the switching parameters of the dynamic behavior of the power transistor is bound by 3 parameters. Forward bias safe operation, a reverse bias safe operation, and a breakdown sustaining. The designer of the given application may be carefully under the no circumstance with the transistor will operate with a curve to provide with a data sheet severe damage if the destruction occurs. Operating point moves outside specified limits. The data of the forward by safe area curve is based on maximum junction temperature of 150 degrees plus Celsius is bound with the 4 points shown in the BVCEO basic minimal maximal allowable voltage, ICM maximal allowable collector current, second breakdown, maximum power dissipation pulse width. Typical FBSOA. Your FBSOA curve is expressed with a defined maximum safe operation area given the device parameter dependent on the shift geometry of the process, build with the transistor, particularly with the emitter fingers. Parameter is extremely important with the high influence of the current spread over the graph of the silicone matter effect with the turn on with the current starts to flow with the peripheral with the emitter with the finger with the depicted with the Figure 8 with the RBB increases as we move through with the turn with the emitter finger. Base emitter junction is now fully forward biased during the first microseconds consequent with the current density of the maximum edge of the junction and the emitter becomes prone to local hot spots. Since the parameter of the temperature of the dependent with the constant power of the the forward bias SOA depends on pulse width. The pulse with very short with a below 1 microsecond curves of the extent of the BVCEO below with the transition specifically designed switching application. Typical forward bias SOAs test circuit given with the Figure 10. It's forward bias, force bias, safe operating area. In Figure 10, give the care most observe the void of overheating of the silicon referred to for the test of a particular important short pulse with a higher energy content. Since the pulse can be generally local hotspot within the silicon sheet, even in the case of the temperature stays at high ambient temperature. Since the forward bias safe operating area testing damage transistor one mode to not reuse the device to expose the characterization procedure. On the other hand, use the conventional power supply with the bias the device, but not recommended since they do not have the capability of accurately controlling either pulse width of the current amplitude with the preferable with the conventional equipment designed for the purpose of built for the specific test jig with approximate dynamic performance for the evaluates limited number of devices. Figure 10 shows the typical forward bias safe operating testing circuit. Show the control of the into a transistor. The reverse bias safe operating area curve of the defined maximum current voltage transistor sustaining base emitter reverse is depicted in the typical test given in figure 11. The parameter essential for the analysis of the breakdown with the dynamic condition of the device locked by an inductor. The test is normally preferred with a clamp connected with the cross. The emitter collectors are limited with the voltage within by BVCES and BVCEX. A device under test. In this case, the transistor is not avalanche. Most energy stored with an intuitive inductor dissipated with a clamp circuit. As a matter of fact, with the voltage clamp used for the transistor sustained with the current voltage drift only with the during the collector of the current full time. Same parameter evaluated without providing the voltage clamp with the transistor will be forced along the avalanche region, and all the energy accumulated with the inductor will be dissipated into the device under the test. The condition forces more than the stress of the silicon current with the following. During time of the collector current fall time under avalanche condition, extreme care must be observed with performing such a test since the transistor rapidly destroyed by the current with not carefully limited with the external circuit of the chain with the rule of the tested circuit slowly increase the voltage clamp with the transistor go with the avalanche current with being limited to pulse width applied with during the charging time of the inductor. The reverse bias safe operating area test is sometimes named sustaining breakdown when it's performed unclamped inductive switching of the collector voltage clamped by the BVCES. Alright, figure 12A shows a micro photograph of the power transistor dam of the reverse bias safely operation hotspot silicone crack. Alright, cross-section damage should be figure 12, showing silicone melts, top side wafer, bottom side hotspot. Power device behavior. The reverse bias characteristic power transistors are split with the two families, leak current and breakdown. Generally speaking, leak current tests do not generate high stress at the tip unless the transistor is under the test with a voltage capability below the voltage bias. A matter of fact, since the bias voltage is defined by prior force across the junction, there is no snapback, but the character of the test circuit remains stable. On top, leakage current with a microampere range for the modern silicone power transistor power generated during the test cannot damage the tip. An example, let us assume ICEO test is performed at 400 volts maximum current with 100 milliamps. Microamps yielding at 440 milliwatts in junction. This value is well within power handling capability. Transistor cannot be damaged device. However, through a providable, reliable information leakage test character other than neither breakdown voltage nor avalanche mode of the bipolar transistor for the behavior of the analyzed meaning with the safe operating area test is discussed above. The transistor is based on the BVCEO with the current voltage characteristics exhibited with the snapback effect with the collector and emitter voltage jumps to the breakdown test point with defined with a higher current phenomena illustrated in figure 13 and prone heavy uncontrolled oscillation due to the negative impedance which are developed from point A to point B. Such behavior can be observed with a curve tracer by limiting the power dissipated with the transistor. Power transistor characterized among the other parameters by setback depicted in figure 14. Under no condition can a transistor explode with the voltage current above the maximum rate provided with the data sheets. Because of the current source used to perform the breakdown test, high voltage compliance, and in this fact, the open loaded voltage must be higher than the maximum breakdown voltage one expected to characterize. It's not easily to make oscillation free with the load is very variable. The problem can be occurred with using anti-oscillation network right across the transistor electrodes, but the device of the damage destroyed by the current arises with maximum value allowable for a given chip. Alright, the values are R and L. Typical anti-oscillation network. It's also possible the capacitor connected across the collector base of the transistor under the test generate local AC feedback, although the recommended with keeping in mind the current associated with the transistor, the high gain transducer amplifier inductor capacitor network connected across the generates high frequency oscillation, which will make BVCO tests impossible. This is one cannot define accurately with a parasitic inductancy straight capacitance existing testing circuit for not even the capacitive feedback across the transistor. Inductor L with the transformer T can be built around the toroid, which high permeability for ferrite material, typical application given in figure 16. One must point out with a design such as an anti-oscillation network vary depends on the test system breakdown and system measure breakdown. Consequently, it's not easy to modelize an accurate circuit of several attempts usually necessary to tune with the network to give it an environment. Another issue of the VCCO test is the discharge story and capacity of the transistor. The tests are carried out with the automatic instrumentation capables can be such several meter in length and strength capacity becomes non-legible and charge up the BVCO. When the current source is disconnected with the device, if the source it has a finite settling time, the current does not stabilize program values less than a few tens of microseconds. Current coming from the disk of the tray capacitance cannot be controlled, but it may damage the chip with a few microseconds, particularly true with the BVCO tested depicted in figure 17. During the negative Cohen slope of the collector emitter voltage collapse, discharging the tray capacity with a delta V from A and B, yielding a peak current above the program value. Assuming the volt 6 and volt 60 volts of total series resistance with a 10 ohm, with the peak current flowing from the storage straight capacity to the capacitor second 1, capacitor second 2, depicted in figure 16 is 6A. Other hand, most automatic testing only connect with a tester coaxial cable 5 meters long. In this case, the total straight capacity combined with the power sense is 100 Pascal farads, yielding with the time constant. And during the amount of time the transistor must dissipate energy accumulated with the capacitor second 1 and 2. Value cannot damage the transistor circuit with the oscillates at a voltage. Resultant voltage can make higher with a high voltage transistor the energy arrive at the value above the maximum capability of the junction. As example, let us assume a resultant voltage of 500 volts and so many 125 microjoules. Of course, the power transistor can easily handle the same amount of the energy. Same transistor rapidly damaging the energy generated with the transistor in favor of the breakdown mechanism. As a matter of fact, during the uncontrolled oscillation mode of the energy developed in the circuit will dissipate in very small of the die with the yielding of the high current density, which in turn generates a hot spot with the silicon. Ultimately, silicon may melt, the device is destroyed. This is consequent of the multiplication factor M is discussed above. Consequently, I recommended to reserve the breakdown test engineering characteristics and purpose of leakage current testing, forming, inspection, have the breakdown parameters fully tested with the several biases, case temperature during the development of the new power transistor, regular sample that provided statistic producing a level to make sure that the device is fully guaranteed, limited published data sheets. Parameter definitions. Off-condition parameters are split into two families: leakage current of the breakdown voltage, but are characterized during the development of the transistor. Testing during the final testing process, the voltage spans from low as 6 volts of the BVCO or high as 1800 volts of the BVCBO. Leakage current ranging from a nanoampere to 1 milliampere at a room temperature. Alright, breakdown voltage or BVCO, reverse collector emitter voltage base, open under given collector current bias. Reverse collector base voltage BVCBO, collector base voltage emitter under given collector current bias. Reverse collector BVCR, reverse collector emitter voltage base connected to the emitter with a low ohm resistor under given collector current base. R's must be located as close as possible to the device under test. The BVCS, or reverse collector emitter voltage base, shorted to the emitter with the under given the current bias. BVCX, reverse collector emitter voltage reverse base emitter bias given the under collector current bias. Reverse collector emitter voltage forward base emitter bias given the collector current bias. Reverse emitter bias voltage collector open given the emitter current bias. Leakage currents ICEO collector to emitter circuit current under reverse collector emitter voltage base open on. ICBO collector base current under reverse collector to base voltage emitter open. ICER collector emitter current reverse collector emitter voltage base connected emitter by low ohm resistor. ICS collector emitter current under reverse collector to the emitter voltage base shorted to the emitter. ICEX collector emitter current under the reverse collector to the emitter voltage reverse bias to the emitter bias. ICY collector to emitter current under reverse collector to the emitter voltage from forward base to the emitter base bias. IEBO emitter base current with the reverse emitter to the base voltage collector current open. Alright, annexes, E is electrical field, E1 minimum energy, ionizing collection, EG band gap energy, Q electron charge and electron density, NP electron density, the positive region, L means of free path, M avalanching multiplication period, AN alpha N ionization coefficients of electrons, alpha P ionization coefficients for holes, table breakdown, material gamma breakdown, electron voltage centimeter, bibliography. This was a quick on semiconductors, and we were probably under this one right here. Let's see if it's the same page. So we open this page. This was understanding power breakdown diameters, and this was author not applicable. Understanding power transistor breakdown parameters.